Hello, everyone. First of all, I would like to thank the organizers for giving me the opportunity to present my work here. So today I'm going to talk about anisotropic scale-separated AdS4 flux vacua, and this presentation is based on this paper that was out last year, and V2 is going to upload it soon. So what is the motivation behind this paper and this presentation? So during the last 1.5 years, actually, people have been trying to test the distance conjecture on the DGKT CFI constructions. And what we observed was that the conjectured parameter gamma, which should be order 1, in these models was way smaller, was like below 0.1. However, we performed a similar calculation to these cousins of DGKT models, which are 3-dimensional, and we included an anisotropic internal space. And we found out that the gamma parameter was larger. It was not order 1, it was not even close to 0.7, but it was larger, okay? It was above 0.1. So we came up with the following idea: what will happen if we find anisotropic solutions to DGKT and then calculate again the distance and test the distance conjecture and measure gamma and estimate gamma? Will this improve the value of gamma or not? So in our attempt to answer this, we discovered new families of DGKT, of solutions, of flux vacua solutions actually. And in the end, we find a dependence of gamma on the anisotropy. Okay? This is what we're going to present. So let's get started. I guess that all of you have heard about scale separation. So in order to hide the extra dimensions here, what we impose is that the Kaluza-Klein scale and the scale of the external space, the AdS radius in our case, they decouple. And this, when they decouple, this will create a large energy gap. And especially in our setups that we will study, we can take a parametric limit that where this energy gap becomes huge. As you understood, I will talk about DGKT setups. I know that there are several people who don't really trust and believe these constructions. I will not make any strong arguments on that. We just study this effective theory, which has very special and unique characteristics, and we're trying to understand it actually. So the DGKT setup is a solution of 10D Einstein of 10D supergravity equations, type 2A actually supergravity equations, with smeared orientifolds. Okay, this is crucial, the smearing in these setups. The effective theory, the 4D effective theory, can be described by n=1 supergravity. And when we perform the dimension reductions and study the 4D effective theory, we find that all the moduli are stabilized. There is an unbounded flux, F4, that we will explain how this remains unbounded. And for large values of this, we can have a classical solution. So the volume is large. The coupling is very small, GS coupling. And and we are at scale separated regime. The tadpole is cancelled by fluxes, actually. And the fluxes are quantized. And we also include the Romance mass and smeared O6 planes. So people actually don't trust these solutions for several reasons. And during the last years, we have made, I think, some progress in order to understand deeper what is going on with these models. So during the 1.5 years, we have developed a method in order to deviate from the Calabi-Yau geometry that is used in DGKT and produce some localized solutions, even to the 10D supergravity from the 10D supergravity perspective. But we have not yet seen, for example, the intersections. So far, those solutions they don't have like any problem. Other people have tried to see if there is an M-theory uplift, and they find actually that we don't have to use orientifold planes, or we don't have to use Romance mass in order to perform an M-theory uplift. So there is evidence that this might be possible to go from the type 2, the type 2A setup to M-theory. Apart from this, we have also constructed models which are similar to DGKT in the sense that they do have all these properties of DGKT. They include Romance mass, smear sources. There is a free parameter where we can take it to infinity and go at classical regime and have scale separation. And we have also found the cousins of those constructions in type 2B with smear sources again, and cross-checked that they're heterotic, they're dual to heterotic 3D solutions. So we are confident for the type 2B constructions in that sense. So several groups are interested in studying the CFT side of these constructions. From the CFT perspective, the 4D solution, the DGKT, and the 3D solution, they are completely different, and still there are some very interesting results. And more recently, as I told you before, people are trying to test the distance conjecture on these setups. We are interested actually in this, so we're going to use those two papers in order to construct our new solutions. So in this paper, the authors used a probe D4 brane and the modulus of this brane in order to interpolate between vacua. We will see this in detail. And in this paper, as I told you before, we created anisotropic solutions, but these solutions are 3D. So we want to do the same, to use the probe D4 from this setup and create anisotropies in DGKT, and then test the distance conjecture and see what happens to the gamma parameter, which was measured to be 0.06 or 0.07 in the isotropic and the original DGKT. Okay, so a quick review. I don't want to read all these details. I mostly want you to focus on this expansion of the F4 flux. So the F4 fills 3 4 cycles, and in DGKT the fluxes here, these actually are the quanta, they're integer numbers, are isotropic, so they are the same. Okay? The solution is smeared, so the dilaton and the warp factor are constant. The forms are closed and co-closed, so somebody can easily satisfy the tadpole. Yes, and and the equations of motion are trivially satisfied as well. And from this equation, somebody can see that since this is a 5 form in Calabi-Yau, this vanishes geometrically, such that the F4 remains unbounded, and this is unconstrained. So somebody can perform the dimension reduction, start from the string frame type 2B with these ansatz, perform the dimension reduction down to 4 dimensions, and we will focus only on the saxionic part. So the moduli that we have is just the 4D dilaton and 3 internal space moduli, which describe the T2 sizes of the internal space, okay, of the orbifold actually. And this is the scalar potential. So we don't minimize here to find the AdS vacuum. We just focus on the scaling analysis. So in DGKT, we know that those quantities behave in the following way. The 3 F4 fluxes are the same. And if you perform the scaling analysis, you will find that GS is expressed like this. So for large values of n, which is the unbounded flux, the GS coupling becomes very small. Okay, so for large values of n, we are at weak coupling regime. These are the 3 subvolumes. Okay, the product of it is the volume of the internal space. The exponents here are positive, So for large values of n, those become large. Okay, so you are not close to the string scale. If those were order 1, then you would be at string scale. The solution would not be classical. And then somebody can calculate the scaling of the potential of the VEV, the scaling of the KK masses in Einstein frame, and this ratio, which tells you that for large values of n, there is a decoupling between those two scales, and you are in scale-separated regime. So something that we should point out here is that if we look closely at the vacuum expectation value, we know that n is unbounded, okay, and it takes integer values. So for infinite integer values of n, here we create a landscape of vacua which have different characteristics. This means that for small values of n, you are not in the classical regime and scale separation is broken. But when you take it to infinity, you go to a regime where scale separation is restored, and you can trust your supergravity solution. Now, let's try to generalize this. We go and we take different values for the effort fluxes, okay? And 1, and 2, and 3. While in DGKT, those values were the same. Let's keep actually the bases the same, n, and put different exponents, put different exponentials. And then perform the so-called detailed balance analysis, which is nothing more than requiring the terms in our scalar potential or the terms in our smeared equations, 10D equations of motion, to scale the same way. So if I go, for example, here, and I take F1, F2, and F3 to be different, those other terms, which is the scaling of the internal space moduli, the scaling of the 4D dilaton, they should compensate such that those equations are always equal, okay? This means that if I perform this analysis, if I require this, I can go back and write all of my quantities in terms of those 3 fluxes, okay? So I keep this general, and the weak coupling is just the sum of those 3 exponents. If I set these to 1, F1, F2, F3 equal to 1, I restore DGKT, right? From here, we can see that in order to go to the strong coupling regime, the sum of the exponents should be negative, which is a bit weird. And then if you take the product of those subvolumes and make and find the scaling of the overall volume, you will see again that in order to the volume to be comparable to the string scale, again, the sum of the exponents should be negative, which is a bit weird. But this does not mean, nothing prevents us actually from having small subvolumes, like close to the string length, while the overall, like the internal space volume, to be large. We will see this in detail. So we can express again the VEV in terms of these scalings. Now we have 3 actually scales that come from the extra dimensional states of our fields, of our dilaton here in this example. And we have 3 conditions to satisfy in order to find the scale-separated solutions. What we observe actually is that in order to break scale separation here, we do have to go to the scalings of our effort fields and set one of them to 0. Okay? Otherwise, you cannot break scale separation. That was not the case in the 3D example. Now, let's go and impose the following. We require our internal space moduli, the subvolumes actually of the internal space, to be always larger than the string coupling. We want the weak coupling to be small, the GS coupling to be small, and we want the 3 conditions that we have for scale separation to always be satisfied. When we impose this, and we also require these conditions to hold, we find conditions on the scalings of the effort fluxes, which tells us that they should be satisfied in order to be in this regime. If you notice here, there is an equality. So if I set this equality and forget about the inequality, I go back to DGKT, okay? So it seems that there is DGKT, it's like just one solution in this family, and around DGKT, there is a landscape of flux vacua with different characteristics. Actually, all of them are classical and scale separated, but their geometry is different. Their internal space behaves different, okay? So here is a simple example. If I set F1 and F2 to be equal to 0 and F3 to be equal to 2 and F3 to be equal to 3, I see that for large values of n, the subvolumes will behave differently, okay? But still, we are in the large volume regime. Now we go and require the scale separation to be broken. So we want this ratio to be equal to 1, let's say. If we impose this, this tells us actually the conditions, the detailed balance conditions, tells us that one of your subvolumes has to be shrinking. Okay, so at some point for large values of n, this subvolume will reach the string scale. Okay, so you're out. This solution is not classical actually for large values of n, and you should have to satisfy these inequalities in order to be in this family. Then we want to have scale separation, and we want also to have one subvolume to be shrinking. Okay, so for large values of n, at some point it will reach the string scale. Such solution exists actually, and there are other subfamilies of this solution, and people, it seems that they have studied this, and they were interested actually in dualizing DGKT and study type 2A or F theory setups. And the last family that we have discovered is the one when we impose one of the subvolumes to be constant, to be like a string scale, and we want the coupling to be small and have scale separated solution. And again, we find a regime where this can be true. So in the beginning, we had DGKT with isotropic fluxes, okay, and we knew that for large values of the flux, you could reach a classical regime which is scale separated. But here, we saw that was just one example in a whole landscape of flux vacua with different properties, and most of them, actually all of them, except DGKT, are anisotropic. Any questions? So, as I said in the beginning, the motivation was to test distance conjecture in anisotropic vacua. And we have to find like a method to do this. And we will use the method which was proposed by this group of people here, where they employ a probe brain that induces a charge of a flux on either side of the brain. We will see what does that mean. Maybe we can even from now relate this to our potential that we had, because we saw that the vacuum expectation value of this construction depend on the flux. So when you change like a flux unit and like go from n to c to n to +1, you just move and go to some other solution which is in the flux vacua landscape. Okay. So it seems that maybe we can benefit from this probe brain and connect and move from this vacua. Yes. Okay, good. So they introduced a space filling probe D4 brain, which is codimension 1 inside a 2 cycle, and it's transverse to one of the F4 fluxes. Actually, in their setup, they introduced 3, which were all transverse to the 3 different F4 fluxes. But here, in our example, in order to interpolate to different families of vacua, we have to use 1. If we wanted to use 3, that would be way more complicated, but I will explain this later. This table is not completely correct, but we can use it to understand the position of the probe D4 brain and the relevant flux that it will change due to the creation and annihilation of the D4 brain. So the probe D4 is space filling. It fills the external space, and it wraps one direction inside a 2 cycle, okay, of the internal space. And there is this flux which is transverse, okay, to the D4 brain. Maybe it's not clear that D4 with codimension 1 induces a change to F4 flux on either side of the brain. But if somebody writes down the equations of motion, like this, can see that here this is a Heaviside function, so it takes values 0 and 1. One can see that when you cross, like this point here, this can be either 0 or this can be either 1, which means that there's a difference there is actually a difference to the flux on either side of the brain. If we employ this and just use one D4 brain, our fluxes will change this way. So since there is no D4 brain transverse to those fluxes here, they will remain the same. But if I create and annihilate this D4 brain here, this F4 flux will change by flux 1 unit. How do we do this, actually? How do we do this? This is not like a decay mechanism. Those vacua are supersymmetric. This is a technique that we use in order to measure the distance and interpolate between the flux vacua that we discovered before. So in order to do this, we will use a modulus which corresponds to the position of the D4 brain inside these 2 cycles here, okay? You can think in the following way. You can think that this 2 cycle is like a sphere, and the modulus, this modulus psi, corresponds to the radial coordinate. So if you are at the south pole, for example, this is 0, and then you can think that this expands, this becomes large, and then this becomes again 0. Okay, so this is the way how the authors interpreted the existence of these modulus inside the 2 cycle. If we do this, actually, we can write down the metric near the brain. We can perform the pullback. We can find the dBi action. We can expand. And we see that in our EFT construction, we have now one extra modulus, okay, which corresponds to the position inside this cycle. So now we have extended actually our moduli space, and we force actually this modulus to move inside the 2 cycle and create and annihilate against itself. And this process gives us back every time we do it 1 flux unit. Okay, so if we perform this several times, we add to our vacuum expectation value +1 units. Okay, and we jump to different vacua. If we start with a random, let's say, ansatz for our F scalings, for example, if we take I don't remember what is here. If we start from an ansatz with F1 to B0 and start from this family and perform these jumps again and again, we change the value of the internal space. Actually, we change the isotropy of the internal space. Initially, scale separation was broken. Here, we restore scale separation, and this solution belongs to one of the families that we found before. At some point, we will reach a region, actually, a regime where all these solutions or all these vacua are classical, the solution is classical, and are scale separated. They're all anisotropic, okay? And at some point, when we perform like several such jumps, we will exit this regime and we will go to vacua where are not classical. Since here, for example, the modulus is equal to is proportional to the string scale. So we are interested in investigating and interpolating between these vacua, and we would like to measure the distance actually from the first vacua to the final one, to the boundaries actually, the vacua which are the boundaries of this regime. Here in this example, I just have used that my n is 2 in order to show this simple example. But in the end, we will see that the solution actually, the gamma is independent of the n, but it depends only on the scalings that we choose. So I showed you before the effective theory that we had. We started with the saxionic part, which was the 4-dimensional dilaton and 3 moduli, which describes the sizes of the internal space. And we added an open string modulus. Okay? So we know the metric of our moduli space. This is the point, and we can go and measure the distance. So we write down the metric, and we see, for example, it has this form. This is like a redefinition of the open string modulus. For the isotropic case, it would be very simple because we could go to the distance and just set sigma 1, sigma 2, sigma 3, which are the canonical normalized internal space moduli. Those would be equal. So we would have left just with this exponential, and we would be able to recognize actually the geometry of our moduli space. However, here in our case, the moduli are not equal. Okay, so we have to perform some shifts in the internal space, which are very crucial in our calculation. So we perform like an O4 rotation, and we bring the distance to this form. We perform again some redefinition that I don't write down explicitly, and in the end, our distance has this form, and from here we can recognize actually what is the form of what is the geometry of our moduli space. The geometry of our moduli space is a hyperbolic 2D space times lines, times 3 lines. It is easy to see that in the isotropic case, the moduli space would be H3 times 1 line, okay? Because the S's, the S moduli would be the same. So now what we have, we know exactly the path, and what we want to do is just go to the boundary, to go to the to the first and the last vacuum in which we want to interpolate. And since we know everything at those vacua, we know the scaling, we can calculate actually everything. So the delta, the distance, is expressed as the sum of these coefficients, okay? And these coefficients are defined as the boundary. So if I go at the boundaries, I can just write down these coefficients, and we see that they strongly depend on the scalings, okay? So this is depend on the difference actually on the scalings between of those two vacua. If we had assumed our internal space to be isotropic, those 3 coefficients would be equal. Okay, and now, in order to calculate actually D1, this is non-trivial, and we have to do some numerics and find out what is the value. And we have to set our value. So in our initial vacuum, those are the values of the scalings that we have. And in the final vacuum, those are the values of the scalings. So these scalings here change because of the D4, which every time which creates and annihilates, it leaves behind a flux. We can write down the ratio of the KK masses, and we see that it depends on the difference of these scalings, and we write down actually the geometric distance. Of course, we see that we can go to infinity. We can take n to infinity. N is the effort flux, which is free, can be taken to infinity. But when we go and calculate gamma, gamma is independent of the values of n, but it strongly depends on the scaling. Okay? So for the ansatz that we have here, we find that is 0.45, which is better than the prediction of the isotropic DGKT. Actually, somebody could go and take different values for the scaling, but this is not straightforward. Somebody cannot go and just change the number such that it gets gamma to be equal to 1, because we have to understand whether we are in a classical regime and whether we can trust our solution. And so that was all. Let me sum up. So we showed that the existence of a large landscape of vacua with different properties, okay, with large or small subvolumes and scale separation, which are mostly anisotropic. We employed a single D4 brane to interpolate between these vacua, and we measured the distance between anisotropic vacua in the classical regime and showed its dependence on the scaling ansatz here. And then we showed that the gamma coefficient depends as well on the scaling of the fluxes, but it does not depend on the value of n, or on the value of the flux. Some future direction would be actually to see if we can find some regions where, some anisotropic regions where the gamma parameter is order 1, or what is it predicted by the distance conjectures, or to include D4s also to the rest of the rest directions which are transverse to the two F4 fluxes. In this case, the moduli space will become way more complicated, but I have performed a very sloppy calculation, and I have seen that in this case, it is easier to find values for gamma which are closer to 1. And why not perform like the back reaction for anisotropic constructions? That would be interesting, and this might allow us to reveal some back reaction or like some intersection easier compared to the isotropic case. Thank you. You can think about it like this. You can think, yes. Yes. Actually, we don't know what is the specific geometry of these two cycles. So yeah, the factor does not change the result. I can tell you why. So if you go, this is very crucial. So if you go to the moduli space here, you will see that there is this function here which defines the geometry. So if we had like a sphere, actually, yes, that would be something like a trigonometric, like cosine psi. However, when you go to calculate the distance, I have not written this here. All these terms appear as logarithms. So this means that even if you change the factor, actually you will have a log. It will be like a sum of logarithms. You will have like log of this function plus log of n to some scaling. And since n can be taken like to infinity, it will always dominate over this coefficient which describes your geometry. Yes, but the crucial difference would be to add more D4 Pro brains to the rest of the directions. That would change the moduli space actually, but not the form of the cycle. Yeah. Yes. Yes. My proposal. Yeah, my proposal actually here was that in the isotropic DGKT, we find it to be 0.06 or 7. When you add anisotropy, you can see that the value actually depends on the scaling. The value of gamma depends on the scalings, which this is translated to the anisotropy. Okay, so maybe there is some parameter space of these scalings where you can make this to be order 1. Yes, I don't know if you can make it larger or not. Larger than 1. Yes. Okay, okay. Yeah. F1, I don't know. I mean, even, sorry, again? That's true. But even if you have like, even if you have F1 or like the rest of Fs to be 1, the GS, you said decreases, increases. Yeah, I see what you mean. I see what you mean, yes. Yeah, but you can have, you can set like your Fs equal to 1 and still take n to be very large. You will find the same behavior, right? So you want to keep n constant and change the scalings here. I mean, this will make the GS smaller, even smaller. Yes, but even if you keep the scalings here constant and make n large, again you will get a small GS. I don't see constraints on the scalings because whatever value you take, yes, yes, yeah. I don't actually. If you take a F1 to be arbitrarily large, I don't know if you can see what happens here. There is like a factor. You mean the ratio here? If it's very small, if it's very large. Yeah. Yes, but also this parameter here, C, depends on the scaling. So this depends on, but again, yeah, I see. Yeah, I don't know how, if there is a constraint that comes from this.